Okay, hi folks, how's it going? Good to see 133 of you out there so far. Good afternoon, hello. Hi. Okay, so what I'm going to do is just go straight on here. I haven't activated the iClicker at the moment, so don't worry about that right now. I do just want to make one announcement, and that is I've just been looking at the Achieve assignments, and so this afternoon next week's will come online. Just looking at my timetable here for Ecology 5 and 6. No, sorry, for Ecology 3 and 4. Okay, I'm going to make next week the last Achieve assignments. Okay, I'm not going to set them in the last week of lectures to give you more time to think about exams, etc. Okay, so next week will be the last Achieve assignments. Okay, great. Good. So what I'm going to do here is, let me just activate my laser pointer. Going to pick up from where we were last time, okay? And you know, as I've said lots and lots of times before, if we're behind in lectures, don't worry, we'll get through what we get through. Lectures will only, exam will only contain whatever we get through, okay? Are we using Connect? Are we using Connect? I don't know what that means, sorry. Okay, so iClicker isn't up yet. Yes, no, iClicker is not activated. So don't worry about that, okay? I prefer to sort of push on with time. What we were talking about at the end of last lecture was we were just starting to talk about climate. We were in the first of the ecology lectures, and particularly concentrating on the physical environment of the Earth and how that affects species that live upon it. And we were talking about this distinction about weather and climate. And what I want to talk about next is what is it that makes the Earth warm up, okay? And so we just got a couple of minutes video that will start off with this, and I can't do it when I've got my laser pointer activated. There it goes, okay. Oops, hang about. One thing I'm going to do here is I'm going to stop here. Sorry, I'm going to stop sharing my screen because I forgot to hit the video share option, which means you won't hear the sound. So let me do that again. Okay, share audio, screen 2. Okay, this time we should get the audio with it, okay?
The energy that drives global climate patterns ultimately originates from the sun. Of the incoming solar radiation, about 30% is reflected by clouds and atmospheric gases and by the surface of Earth. The reflected solar radiation makes Earth
every time I touch my mouse, it'll stop.
The rest of the solar radiation is absorbed by gases in the atmosphere and absorbed by the surface of Earth. When an object absorbs electromagnetic radiation, it heats up and in turn re-emits electromagnetic radiation, but in much longer, less energetic infrared wavelengths. In this way, a relatively large amount of energy is emitted by Earth's surface. Some of the emitted infrared radiation is transmitted straight through the atmosphere and lost to space. However, the rest is absorbed by gases in the atmosphere. These molecules are warmed and then re-radiate photons, many of them back to Earth's surface and to clouds, where they're again absorbed. This continual process of reabsorption and re-radiation keeps energy within the Earth's system, heating both the Earth's surface and the lower atmosphere. Radiant exchange between the surface and the atmosphere explains why Earth's surface is warmer than it would be if there were no atmosphere at all. Ultimately, however, the radiant energy emitted into space balances the amount of incoming solar radiation that is absorbed by Earth's surface and atmosphere. The warming of Earth's surface that results from the retention of energy by the atmosphere is called the greenhouse effect. A subset of gases in the atmosphere strongly absorb infrared radiation. These so-called greenhouse gases include carbon dioxide, methane, and nitrous oxide, as well as water vapor. The greenhouse effect is a natural effect, but also one that human activities are influencing. By burning fossil fuels and through other activities, humans are increasing the atmospheric concentrations of greenhouse gases, especially carbon dioxide and methane. This is increasing the radiant exchange between Earth's surface and lower atmosphere, raising the temperature of both. With its greenhouse gases, Earth's average surface temperature is 17 degrees Celsius, rather than minus 18 degrees Celsius, which it would be without an atmosphere.
Okay, that's quite a useful video, I think, just explaining some of the basic processes that are controlling how Earth warms from the sun's energy. Okay, so this is a sort of summary of that process. So the important point, well, let's go back a step. So the important points are here that the sun is warming the Earth. Some of that is reflected back into space, okay? But a portion of that is absorbed by the atmosphere and it warms the Earth. And as it radiates back out, it's a different wavelength. It's a longer wavelength. And that interacts with a portion of gases in the atmosphere, actually a very small portion of gases in the atmosphere, because those specific gases interact and vibrate at those long wavelengths and re-radiate that energy in all directions, some of which goes back towards the Earth. So that's warming the Earth. And these are the key gases in the atmosphere that are playing a role there. Carbon dioxide, which we all know about, and methane. Water vapor also plays an important role, and nitrous oxide. Okay, but carbon dioxide and methane are the key drivers that we as humans are adjusting as part of this in changing global temperature. This next portion is illustrating facts that most of us are very familiar with, but just reinforcing the point that the warming of Earth is not the same everywhere. One of the key things that is affected is what latitude you're at. So latitude is how many degrees you are away from the equator. If you're at the North Pole, it's 90. If you're at the equator, it's 0 degrees. And so less energy reaches the Earth's surface nearer the poles. And the reason for that is that the sun is striking the Earth at a more oblique angle. And what that means is two things. First of all, that the distance that that sunlight travels through the atmosphere is greater at high latitudes than at low latitudes. So a smaller proportion of it reaches the Earth's surface because more of it is interacting with the atmosphere. The other key point is that the Earth is at an angle with respect to the sun's rays. So the area that a given amount of sunlight is, given area that's receiving a given amount of sunlight is larger at a high latitude. So therefore, there is less sun energy per unit area of Earth to warm it. So two key factors that are affecting that process. And so what that means is that where you are on Earth is the temperatures that you experience vary with respect to latitude. You go to the tropics or near the tropics for a nice sunny beach holiday rather than Greenland because it's nice and warm down near the equator. So there are modifications around this. This isn't strictly latitude. there are other things that can be controlling it, such as, for example, here in the Himalayas, you're at a pretty low latitude, but extremely high altitudes. And as you go higher in altitude, there's less air, it's less dense, and so you're colder. But in general, it's warmer near the equator. Also, so it's mentioned in here that in text that the northern hemisphere is about 2 degrees warmer on average than the southern hemisphere. There's a variety of different reasons of what can be playing into that, but probably one of the largest factors is the area of land mass in the northern hemisphere is much greater. So the sun's rays heat up the land, which also then heats up the atmosphere above it. In the southern hemisphere, the ocean, the greater ocean area, acts more like a heat sink. It absorbs that energy, and then it's redistributed, some of it going down into deep oceans, etc. So it's absorbing more of that temperature, less of it going into the atmosphere. In relation to this, there's also a very general distribution pattern to rainfall around the Earth. And as you can see in this diagram here, around the equator, it is generally wetter than at distances further away from the equator. So this little bar here shows you average annual precipitation. So number of centimeters of precipitation, either rain or snow or hail, in different areas. The darker you are, the more precipitation you get, and this middle band here has got the highest precipitation rates. Now, there are other modifiers to this as well, of course. You know, you look up here, for example, and it's a wet area there. That's because it's mountains adjacent to the ocean that's causing rain. Are seasonal changes in temperature on land reflected in ocean temperatures as well? Or is it too big of a heat to act? Yes, they are reflected in temperatures. They're also heavily modified by the types of currents that you have. So, for example, we'll talk about this a bit later on, but so I'm from the UK, obviously, and if you go in the water there in the summer, it's about maybe 14 degrees Celsius if you're lucky. If you went to that same latitude over here in Canada, you would be in not much above freezing. And that's because of the Gulf Stream that circulates in this direction and brings warm temperatures. So there are other modifying factors, but yes, there is seasonal variation. Like in Long Island Sound, it gets up to maybe about 24 degrees Celsius, so the low 20s in the summer. In the winter, it gets down to maybe 3 degrees Celsius or so, 4 degrees Celsius. Okay, so variation in rainfall patterns in a very general sense, okay? And we'll talk a little bit about what sort of processes are containing that. The driest places on Earth are actually at around 30 degrees north and south of the equator, okay? So here, the Sahara Desert, for example, it's not on the equator, it's offset from the equator. We'll talk a little bit about that process as well. So as part of that, we need to consider atmospheric circulation patterns, okay? So solar energy determines the circulation patterns of air in the atmosphere. And as you're probably aware, as you warm some air up, it becomes less dense and it rises. So that's why if you go in a hot air balloon, you have a big, burner that is heating some air. That air is lighter, it rises into the balloon and then lifts you off the ground. But as air rises in the atmosphere, it also expands and it then cools down. And cool air cannot hold as much moisture in it as warm air. So if your warm air that's been near the ground, evaporated lots of water from vegetation or the ocean or something, as you rise up, you expand, you cool down, and then you have to release some of that moisture, and that creates precipitation. Okay. So in a very general sense, this is some of the process that goes on that explains that global variation in precipitation pattern that we just talked about, okay? So if you imagine here that you have the Earth, and near the equator, you've got strong sunlight going through a small relatively small amount of atmosphere and contacting a concentrated landmass near the equator, so lots of heating. That is evaporating water that's on the surface there, and it's getting hot. That air is getting hot, so it rises. That's what these here are showing. These show general circulation patterns of the air. So near the equator, you've got strong heating, rising of air. That is then releasing all of that moisture that it contains, and that is what's giving, that's what resulting in that equatorial high rainfall pattern. Well, that air has to go somewhere, okay? So it circulates up and it cools down. So you've got this high, strong heating here, rising, and it circulates and eventually goes down. So you get this circulation pattern. So it circulates at the equator, goes towards about 30 degrees, and there's a general sort of descending air around about 30 degrees north, 30 degrees south. Okay, this is called a Hadley cell in this equatorial region.
Professor, why does the cooling air move like to the side rather than just coming straight back down?
It can't come back down because there's so much air coming up. So,
Okay.
you know, if there's a strong updraft of air, it's got to go somewhere else, right? So it can't come down because of that heating air in its place. Okay.
Yeah.
So what that means is that at these 30-degree areas, you've got cool air that's descending, but it's been dried out because it's dumped all its rain already, right? So these are dry areas at the offset from the equator. Okay, and that's why when we looked at that precipitation pattern, you have these major deserts such as the Sahara that are offset from the equator. Now, as you move to higher latitudes, you get some reciprocal circulation patterns occurring as well. Okay, so there's another pocket of rising air here around about 60 degrees, leading to some wetter conditions in temporal areas. That circulates down as part of this dry area here at 30 degrees. It's also descending in polar regions, okay? So poles are actually deserts in general, which seems strange because you look at a picture of the Antarctic or the North Pole or something, and it's just like solid water in terms of ice or snow. And the reason why that is that even if there's a low rate of precipitation, once it arrives there, it's not going anywhere because it's generally just frozen, and so it accumulates. Even though the precipitation rates are lower than if you move to a low latitude. This is a video that I put in here from YouTube. That I'm not going to start it here, but it's one for you to watch at home. It explains some really nice NASA satellite data accumulated over a 20-year period that shows some of that global variation in rainfall and explaining how some of that comes about. Okay. Now, one thing that we haven't talked about so far is that this is a sort of simplistic up-down movement of the air, but it's made more complicated by the fact that the Earth is rotating. Okay, so the Earth rotates from west to east, and that means wherever you are on the Earth, you're moving in that direction. The speed at which you're moving varies depending upon where you are on Earth. So if you imagine, it's a bit like spinning a basketball on your finger, right? If you're spinning at those poles where you might put your finger, it's hardly moving at all or not at all, because that's the point of revolution right there. So here on the poles or the axis, you're pretty much zero speed. But as you move towards the equator, you might be going over 1,000 miles an hour. And there's some little thing on the internet where you can go to your latitude and calculate your speed, etc. So this was, Queen's University is going, Queen's College is rotating at about 700 miles per hour. Now, these movements have some effect upon this general up-down circulation that's going on, referred to as it brings about something called the Coriolis effect. Okay, and so this is a little tricky to visualize, but what you have to imagine is that if you're at the equator here, and you're imagine that this movement pattern is going along, and along this direction, you're moving towards the equator. If you're above 30 degrees, you're moving away from the equator. But the speed of the Earth changes. Does the speed of the Earth move as well as the air rising? Yes. So basically, if you're an air mass over land here, okay, you're moving essentially with the Earth. Okay. So here, as well as you actually have a movement in this west-east direction. Now, as you move away from the Earth, everything else underneath you is getting relatively slower, okay? So what that means is that you're actually sort of, as you go away, you're moving ahead, okay? So these winds here are moving away from the equator, so they actually shift ahead a little bit. The reverse is true if you're moving towards the equator, okay? So here, everything underneath you is getting a little bit quicker, so in effect, you're falling behind as it goes ahead. It's kind of tricky to visualize, but this video does quite a nice little job of explaining it. I quite like it, okay?
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving the example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placement of jets inside the toilet. But that's it, that's the Coriolis effect. If you like this short and to the point video, give this video a like, and if you want to see more videos like it, why not subscribe? I'll be back next week with another video, so until then, thanks.
Okay, so that's kind of cool, that video, I think. So if that confuses you, you can go back and I've given the link to it, etc. So you can sort of think about that more carefully. Need to. Yeah, cool. It is a good video. The general way it's done, it reminds me a little bit of, I don't know if you watch like you suck at cooking thing on YouTube, but my daughter and I like watching that. It's a general similar type of humor to it. Anyway, the so those surface winds, they also have a huge effect on the surface ocean currents. Okay, I was talking about the Gulf Stream earlier on. Okay, so sorry, if you imagine that like in the northern hemisphere, for example, these are the wind patterns about between 30 and 60 degrees, with air moving away, okay, away from the equator, and it moves ahead. Between 30 and degrees and the equator, you're doing the opposite. You're moving towards the equator. So as you go towards the equator, you fall behind, right? So that generates this sort of type of direction, and that is a major driver of the major ocean currents on Earth. So here, these black bars represent these equivalent wind patterns, and what it's doing is it's pushing water up here in this direction. Now, eventually, it's going to collide with another continent, and at that point in time, it obviously can't go any further. It has to, go in one way or the other. So, and that depends a little bit on the shape of the land and which continent you are on, and factors such as that. Some of that is deflected in the Atlantic up above, past the UK, and up towards Norway, etc. But a major part is circulated back down. So you've got this pattern going on here. Okay. You go down to the South Atlantic, you got this pattern going on. Pacific, okay, this direction, and then in the other Northern Pacific is doing this. There is also a counter current, equatorial current, because all of this part here in South America, where all this water is colliding with the continent, some of it is deflected back along the equator. But this is really important because it's the movement of water. Remember, I said that water absorbs heat a lot from the sun. So in this area, it's really getting heated up in the Gulf of Mexico, etc. And then when it's driven up here, it's transporting all of that heat to high latitudes. It has a major effect on adjacent land masses, what kind of a water current you have in your vicinity. Either, as I mentioned here, these really cold currents, so you have really cold conditions in northern Canada, or in Europe, by comparison, given your latitude, you're quite warm because all of this warm water is being pushed up here, okay? All of this is related to Coriolis forces and the air circulation patterns above it. And that's why the Pacific is colder than the Atlantic. It depends where you are. You're talking about on the US coast. If you're talking about the Pacific, that's because you have a cold current coming down California, right? So it's the same there. So clockwise in the northern hemisphere, counterclockwise. Yes, correct. Okay. Okay, so another major modifier of Earth's temperature patterns is obviously seasons. Okay, we're going to spring now. Summer's coming. It's going to get warmer than it was a few months ago in the middle of winter, and that is due to the tilt of the Earth on its axis with respect to the sun. So as the Earth rotates, it goes around the sun. Okay, once a year. And if you're in the northern hemisphere, as you go into when the Earth is tilting away in the northern hemisphere from the sun, then you're not experiencing, you're getting less sunlight, basically. And if you're in very high latitude, you get no sunlight whatsoever, so you're not being warmed at all. Whereas by the time that we come around to summer, the northern hemisphere is tilting towards the sun, so we get more direct sunlight from the sun, which warms up the Earth more. The opposite, of course, if you're in the southern hemisphere. Okay, so the tilt of the Earth's axis relative to the sun is important for these seasonal variations that we experience. Now, there are other factors that can modify the physical environment of the Earth, other than these latitude effects, seasonal effects, and the circulation patterns of the air and the ocean. These include the Earth's topography. So that means the shape of the surface of the Earth. So mountains or deep oceans, for example, as part of the topography. Vegetation can affect the physical environment, and human influences. So let's talk about some of those. First, we'll talk about topography, right? And an important factor here is rain shadow. So if you can imagine an example where air is moving off the ocean, it's going to have, it's moving across the ocean, so it has water evaporated into it. If you encounter a mountain and that air is forced upwards, that is similar to that effect we were talking about earlier on, as air moving upwards gets less dense and colder, so it drops, it can't hold as much water, so precipitation occurs. So high precipitation on one side, but once you get to the other side, it will descend, warm up again, but it's lost all its vapor, all its water content. So it's extremely dry, leading to this effect of so-called rain shadow. A really great example of this is in Death Valley, or in fact a lot of, if you go up and down the California, up and down California, if you're on the coastal side of the mountains, the Sierras there, it gets really foggy in the summer, lots of precipitation well, often there's precipitation, and relatively cool. You go on the other side, somewhere like Death Valley, one of the hottest places on the earth and one of the driest places on the earth, because all of that water content is dumped in the Sierras here. Really rainy, big forests like sequoias forests, etc. Go skiing in the winter, things like that. But it's lost all its moisture by the time it comes to the other side. Another way that land topography can affect the physical conditions is when you have a valley effect that can lead to temperature inversions. And these can be really dramatic when you see them in effect. And the effect here is that when you have this kind of like constrained valley effect, the land warms up relatively quickly during the daytime. So it warms up, gains its heat, and because it is warming up like this, air will tend to rise up the sides of the valley, and cool air will descend from altitude to take its place. You've got cold air coming down into the valley. Well, at nighttime, that land will relatively quickly lose its heat and cool down. And then you have cool air descending down the valley side, and that hot air escaping up at the top. So you get this pattern here. So either way, you're getting sort of trapping of cool air below warm air, which is the, sorry, it's my dog being excited by something. So either way, you're getting cool air underneath hot air, okay, which is the opposite of what we would normally experience. And if you go hiking in places where experience this, I've seen this a lot, in the Scottish mountains, for example. You go walking in the early morning and you get this effect where you go high up and then you look down, and then there's this amazing effect where all the clouds are actually below you, because that's where the cool air is trapped. There's a nice video here explaining some of that process. Okay, I'll leave you to watch that at home. This is a nice graph that comes from that video showing how, as you go up in elevation, temperature decreases until you get to that temperature inversion, and then it carries to on decreasing again. Okay. Another modification of topography can come from ocean topography. Okay. And actually, this occurs on the California coastline as well, where if you have wind blowing along the coastline or off the coast into the towards the ocean, you get this effect where it moves the surface water away from the land. Now, we don't have time to go into this in detail, and you might think it's strange that a wind blowing along the coast leads to water movement off. It's due to this Coriolis forces that are involved, and the water causes water to move at different speeds at different depths. But essentially, you get this movement of water away from the coast. It leaves a gap behind it. Something has to move into its place, And so what happens is that water from deep areas comes up and replaces it. You get this upwelling of cold water along the coast, okay? This has two effects. It cools the adjacent land. That's why in California and many places you get these really dense, foggy areas in the summertime. Also, it's really important for things like fisheries and all sorts of things like that, because this water coming up from depth is very nutrient rich. It leads to lots of primary production that then sustains other organisms that feed upon that. The major places on Earth where upwelling occurs tend to be along the western coasts of continents, because of the wind patterns going in this direction here, and the ocean circulation patterns, and this direction that's pulling water away in this direction. That leads to upwellings in these major areas. So Peru is one of the most, off the coast there, major upwelling areas, some of the most productive fisheries in the world. We talked about how also vegetation can affect climate. How does this occur? You know, we hear about how important the Amazon is, for example, in modifying climate in that region, as well as globally in terms of its carbon capture, etc. But forests create a really important cooling effect, and they create wetter local conditions. So how does that occur? Well, when the Earth is being warmed by the sun, when you have a forest, some of that solar energy is being reflected back up into space, as we talked about at the beginning of the lecture. That's called the albedo effect. Some of it is being convective heat loss. So that's the land is getting heat and then it releases it back up into the atmosphere. Both of these processes are going on, but they're modified by forests, because forests have got a fairly low reflectivity. So that's actually sort of keeping some of the heat down here. The convection is also being, there's more heat trapped by the forest, because it's reducing wind flow away, okay, so it's the heat being lost. But that is more than offset by the fact that cooling is occurring by so-called evapotranspiration, evaporation of moisture from the surface of the Earth, but also from all of these leaves. So the trees are bringing up water and evaporating water from them. That creates a huge cooling effect, because as water evaporates, it cools the environment around it, and also to high precipitation. If you then go to an area where that forest has been cut down, you get a modification. You actually lose a bit more heat through albedo and convective heat losses. The surface tends to be a bit more reflective. Air can pass over it easily, so you can lose heat more easily. But that is more than offset by the loss of evapotranspiration. So your major cooling effect when you have a forest is reduced substantially. So overall, you become warmer and there's less precipitation, because less water is being evaporated up into the atmosphere. The last point with these modifying factors, we talked at the beginning, I mentioned human effects on physical environment. And this is related to the so-called urban heat island effect. And this is actually a study done from, I can't remember, it says in the notes, I think I got it from a paper in 2008, of looking at New York City and surrounding areas. And so what's this is demonstrating is that on this graph here, along the x-axis, we have the time of day, okay? So from midnight to midday to midnight again. And then these figures here show in different areas around the city how the difference in temperature in that part of the city with respect to if you went to a rural area away from where it was all built up. Okay, so you're in a sort of, you know, where there's trees and vegetation, things like that. So in other words, if you're 3 degrees up here at midnight, that means that at midnight, in that urban area, you're 3 degrees warmer than if you happen to be, you know, 30 miles or 40 miles away in the country or something. Okay. Now what happens is during the daytime, this difference kind of goes away, and that's because all that urban area, the streets and things like that are absorbing the sunlight. But at nighttime, they release that into the atmosphere, and it warms the air around it. Okay. Now, there's modifiers within that. So this green one here is actually showing Central Park. So Central Park is warmer. You get an urban heat island effect. If you're in Manhattan, but there is still quite a bit of vegetation there, and the effect is not as dramatic as if you go to, this is Ocean Parkway in sort of Brooklyn area, where it's much more built up and much less vegetation, and so this urban heat island effect is much more pronounced. Okay, so warmer at nighttime than it would be as if there were no buildings and things there. Okay. So we've talked quite a bit about the physical environment around the globe and on a more sort of regional basis and how it varies from different parts of the Earth to another. Now we're going to talk about biogeography. And so that's looking at basically the interaction between that physical environment and species that live there. So biogeography is the study of the distribution and diversity of species and ecosystems. So ecosystem is a term that we'll come to in the next lecture. It's the animals that live there plus the physical environment. So it's looking at the distribution of these in their geographic space and through geographic time. Now I've used this term here, diversity. Diversity, there are different types of diversity. What I'm talking about specifically here at the moment is the number and composition of species in this context. So in other words, if you have 100 species living in an area versus 2 species, that's the diversity that we're talking about. Patterns of diversity play out over many spatial scales that are connected in a hierarchical way. Okay, that's illustrated in this diagram here. So if you imagine the Earth going down in scale to just like a local forest or something, woods or something like that. Okay, we have this transition from the global scale to a regional scale to a landscape scale to a local scale. So with the global scale, we can consider diversity, so the global pattern across multiple regions, driven by continental ocean isolation. So this is considering all the species on Earth basically. Okay. You go down to a regional level. Now, an example of this might be something like, what is the diversity of species in the entire Amazon basin, for example? So, many thousands or millions of square kilometers. That's referred to as the gamma diversity. Okay. So all species limited to a large region and comprised of multiple landscapes. So all the species in the Amazon basin. If you then go down to a landscape scale, and we talked about these concepts at the beginning of the lecture last time, the landscape consists of multiple communities. Variation of species from one community to another is referred to as the beta diversity. Okay, so for example, I won't use this. If I think of that Amazon, you can sort of think of the species living in a river, and then the species living in the forest next to it. Okay, they're going to be different species, obviously, but they're a part of that regional and landscape effect. And then you can go to a local scale. Okay, so a single community of species in a local ecosystem. So species that are living together and can interact with one another, such as those living in a little bit of river together. That will be referred to as the alpha diversity. Okay, so these gamma, beta, and alpha diversities refer to different types of scales. In a global context, we can think of animal or organism distribution in terms of biomes. So this again is a very general sort of global pattern that we're thinking about. So biomes a biome is a grouping of ecologically similar organisms shaped by the environment, mainly temperature and water, but there are other effects as well. And they're typically classified by the dominant vegetation that occurs with them. And then often there are many other types of animals and so on that be associated with that. Why is it concentrating upon vegetation? Well, vegetation doesn't move around like animals do, and so it's better reflective of a particular, a certain location because it's not moving around. Different people consider different number of biomes on the Earth, so what you see might depend upon what particular source you're looking at. These biomes are controlled by the physical environment of those different locations. And a way of considering this is using these so-called Walter climate diagrams, okay? And these are quite clever, really. So I've got, so here, 6 different plots, breaking them down into tropical rainforests, deserts, temperate grasslands, temperate deciduous forests, boreal forests, and tundra. So we'll discuss those a little bit. And what it's showing in these graphs here is 2 aspects, precipitation and temperature on average in different months of the year, okay? Now, the clever thing about these diagrams is that they kind of show the plant growing season. So when is it that that vegetation can grow at different times of the year? And that's because on average, vegetation or growing season is typically stops when temperatures get to 0 degrees Celsius. And also, vegetation in general requires about 2 millimeters of precipitation for each degree of Celsius above it. So the warmer it gets, the more precipitation you're going to need because there's more evaporation, so you need more rain, etc. Okay. Now the way that these graphs are drawn are that the scaling, so this is the precipitation axis on here, it's scaled so that for each degree Celsius, shown on the left-hand side, it goes up 2 millimeters, okay? What that means is that when the precipitation line drops below the temperature line, it means it's too dry for growth to occur. If you look at the region here, this is the temperature line, and that precipitation line is way below it. So that means that vegetation growth is constrained during that time. At other times of the year and other places, when it gets below 0 degrees Celsius, indicated by these blue areas, this little shading is offset a little bit, but in general, these blue areas indicate when you're below 0 degrees Celsius. So what these diagrams are showing are that you're outside the growing season throughout the year in the desert. Now, there are periods, obviously, where you get like a massive rainfall, those big flower blooms that occur in the deserts, etc., when that occurs. And then at different latitudes, it's too cold for vegetation growth to occur, and the length of that non-growing season depends upon, as you go to higher latitudes, you get more time below 0 degrees. Notice in tropical forests, precipitation is above temperature the whole time, and you never get below 0 degrees on average. So this has the longest growing season, the most productive places on Earth, where you get high rainfall, high temperatures throughout the year. So how do they show spatially these areas? So we'll just quickly go through some of these biomes. Okay, so I mentioned tropical rainforests. They're most concentrated equatorially in those regions where you have high warming of the Earth, all that air rising up in the Hadley cell, dumping all of its precipitation as it rises and cools. So warm temperatures, lots and lots of moisture, really high growth. So year-round growth at high temperatures and rainfall. The most species-rich biome of all on Earth, okay? Half of all species. I'm guessing that refers to terrestrial species. I'm not quite sure about that, but I would imagine so. And so unfortunately, about 1% of that is being destroyed, chopped down per year so that we can, eat beef and things like that. So that, that's a major conservation concern, obviously. If you move away, remember, if you go to 30 degrees offset from the equator, approximately, you get these desert areas where that Hadley cell is rising, it's dumped all its air, now the air is cooled down and it's descending back down to Earth, but without any precipitation with it. So like along here in the Sahara, for example, where it's extremely dry. So here you have the desert areas, so very dry, very little vegetation, because although it's warm all year, there's no precipitation to sustain high vegetation. Plants and animals adapted for extreme water conservation. Now, some of these areas are offset from, the 30 degrees, etc. And that can also be related to other modifying factors, such as being in the middle of a huge continent, where you're far away from water, for example, or if you're in a rain shadow area, that is inducing desert conditions as well. So at slightly higher latitudes, you get these temperate grasslands. Okay, so they have, they're relatively dry for much of the year. So, for example, here in North America, away from major oceans, so you're not getting so much water or moist conditions, but rich in grass and herbaceous plant species, and support large grazing animals. So, historically, before in North America, a lot of these were lost to farmland, basically. You had grazing animals like this, or you go to the Kruger National Park in South Africa with grazing animals, etc. around there. So it supports large grazing mammals with rich topsoil, but many lost to agricultural for corn and wheat production, etc. Also in temperate areas, we have deciduous forests. So the northeast, the area that we're in, is an example of this. So in Europe, Eastern North America, Eastern Asia, it's a very seasonal, cold in the winter, hot or warm in the summers. So the tree leaves are lost in the winter when you don't have that growing season. Okay, you've gone below 0 degrees Celsius. And so they're losing their leaves. Many more species than boreal forests. We'll talk about boreal forests next at higher latitudes. And a lot of the species that are living there, so species migrate during the winter or enter resting stages. So, at the beginning of May, I put my hummingbird feeders out, and that's because the hummingbirds are, moving from down here up to here. There's migration going on based upon the season. Now, at higher latitudes, you get these so-called boreal forests. Okay, boreal means north, and also you get temperate evergreen forests. So these boreal ones are just above 50 degrees north, so up in Canada. And these are coniferous trees that dominate them. So instead of losing their leaves during the winter, they retain them. Okay, and the reason for that is that their growth season is so much shorter because it's only warm for a shorter period of the year. They don't want to waste time generating those leaves. As soon as it gets warm, they want to be then, photosynthesizing and growing, etc. Okay, so it's thought one of the reasons behind the difference between coniferous and deciduous forests. And you also get temperate evergreen forests. So again, actually, California is another good example of this, where you have the redwoods and sequoia forests that are evergreen in that coastal region, the wet, moist region, but cooler regions down here. Okay. There's also an interesting difference between the northern and southern hemispheres with these. In the northern hemisphere, these conifers are dominated by sorry, in the northern hemisphere we have conifers, whereas in the southern hemisphere they're dominated by evergreen beech trees. So there's a sort of species difference between them as well. And then at the highest level you have the tundra, okay, above about 65 degrees north. These have very low temperatures and a very short growth season. But crucially, they have an underlying permafrost layer. So this is just below the surface of the soil. There is, at a shallow depth, areas of soil that remain frozen the entire year, even during the summer. They receive little rain, but they tend to be very wet, and that's because there is this permafrost area. That water can't drain down through the soil. It gets trapped there, so it's got nowhere to go. So the land remains wet despite the low rainfall. And the vegetation is very short and scrub-like, partly because it can't get deep roots because it encounters at a shallow depth that permafrost layer. So this variation of species around the Earth and how they interact with their physical environment, we're talking about biogeography. The so-called father of biogeography was Alfred Wallace. He lived in the 1800s, and he was a contemporary of Darwin. So he was really, started this whole study of where and when species evolved, and how this was key to their biogeography, how it was key to how they varied around the world. And one of his key observations is the so-called Wallace line that retains his name today. He observed that when you go to this area in Indonesia, around about where Bali is, if you go to one side in Indonesia, you get a typical sort of suite of animals and species that live in that area. But you go across that divide, and the composition of species is completely different. And it turns out that that's because of the movement of land masses over time, and that these have been typically separated, and there's a very deep ocean trench that runs along this line here. Whereas movement of species can occur across Asia at different times of Earth's history based upon different sea levels. There's been connections across here, that's shown by these brown areas. There's no connection across here. So these group of species evolved completely independently from those across here, okay? Now, we touched upon this when we were talking about the evolution of vertebrates. I showed you a phylogeny in the vertebrate lecture showing that when you create a phylogenetic tree of modern day vertebrates, they group genetically, or they have a grouping that's related to the historical land masses. That's reflected here as well. So Wallace identified biogeographic regions that were separated by climate, topographic or aquatic barriers to dispersal. So we talked about that Wallace line, for example. Species assemblages change dramatically between regions. So these are showing different regions of the Earth where have major different species assemblages. And today, it was speculated in his time, but not really accepted actually until the 1950s or 60s, of continental drift. And so we know now that a lot of this pattern is related to continental drift patterns and how groups of animals and organisms have been separated from one another for long periods of time. This relates also to how animals or how different species evolve over time, how they become separate from one another, from a common ancestor. Two of the key mechanisms by which this can occur are so-called vicariance and also through dispersal, okay? So with vicariance, that's indicated by these top figures here. physical barrier prevents dispersal of organisms. And that leads to a division between populations, from which then you have allopatric speciation. So in other words, what this is showing here is that you have species A that is on this group here, so that in this population they can all interconnect. But somehow some division occurs between them. So this is indicating a river in a forest or something, but it might be two continents drifting apart or something like that. So some of the group A, species A, get trapped here. Some of them get trapped here. They can't now interconnect and breed with one another. And over time, they adapt and evolve to the conditions specific to these two different areas, and ultimately may evolve into two separate species. Dispersal can lead to this effect as well. So if you imagine an island with nothing on it that is far away from a mainland, but somehow some of species A managed to drift on a piece of driftwood or something like that, or is blown in the wind, if you're a bird or something, to this island over here, and then they start reproducing. Over time, that separation can lead to the evolution of new species through dispersal. This is related to the so-called theory of island biogeography. And what this theory is showing is that the number of species that occurs in an area is controlled by both immigration and extinction rates. So if you imagine that you're in some sort of isolated island, the more species that can immigrate there and potentially evolve into new species, the greater diversity you're going to have. If some of those are becoming extinct over time, you're going to be losing species, okay? So you've got two counteracting forces there. Island size that you're on is going to have some effect there. So small islands are going to have less resources. So if you're on just like a really tiny little desert island or something, very few resources, it can only sustain so much, right? So if somebody else arrives or a few other people arrive when you're living on a desert island, suddenly you're all going to be competing for those same resources. So there's a greater extinction risk when there are few resources. So if you're on a very small island versus a huge island where, if I can't compete with you to get my food, well, I'm just going to go down the beach somewhere else and try my luck down there, right? So extinction rate is being controlled by island size. So this graph is showing that effect. This is the number of bird species on islands, different islands in the Pacific, based upon their size. So here, Wake Island is obviously a very small island. Solomon Islands, very big area. There's this relationship showing the number of bird species tends to be greater on a large island, okay? So that seems to make sense with respect to the island size effect. The other effect is going to be this immigration rate here. So, many of these islands here, so Hawaii is a great example of this. These are islands that arose back in geological time through volcanic activity. Volcanoes blow out and they create a new island from the sea bed. So there's nothing on it when it first occurs. The only way you can initially get species is new things arrive there by chance or by flying or something. If you're closer to some mainland, you've obviously got a much greater chance of species arriving there. So this is showing, saying that basically if your island is far away, you have a lower immigration rate. That's the general sort of theory. And it's also reflected in this graph. Different colorations of dots indicate that the green ones are islands that are near the mainland. So the nearest mainland to these is New Guinea. If for a given size of island, you're nearer to New Guinea, you tend to have more species on it than if you're these yellow ones, which are far away, okay? So now you have less species given your island size. So it's modifying this general relationship, okay? Species diversity also changes with latitude in many occasions. And one of the most typical patterns that's observed is this relationship that you often get a higher diversity of species near the equator than if you move away from it. So in this figure here, what it's showing is this is latitude, 0 degrees being the equator, so roundabouts here. And then as you go up to 70 degrees in the northern hemisphere, or down to 40 degrees in the southern hemisphere, okay? And it's showing the number of species at these different latitudes for global swallowtail butterfly diversity. A lot higher near the equator than if you move away from that. There are all sorts of arguments and hypotheses, etc., explaining why this may be. And in some cases, one hypothesis might be true. In other cases, another might be true. It might depend, and it's not a fully sort of settled debate. But these are the three main hypotheses. One of them is species diversification rate, species diversification time, and then the productivity of these systems. I've put in the notes below the slide an explanation of those. But the diversification rate argument is saying that the rate of species, rate of speciation is greater than the rate of extinction at low latitudes for two possible reasons. First of all, the area of landmass actually available around the world is actually much, if you looked at a map of the entire world, you actually have a higher land mass around the equator. So that's related to that extinction rate, okay? You got more resources. The other is that also, this is some of the most productive area on Earth because of this, you know, that high temperatures and high rainfall. So you've got a lower extinction rate there in terms of more resources. Another argument is species diversification time. So because around the equators it's warmer, when we've gone through ice ages and back out, etc., you're not getting species being extinct because everything is covered by ice. They've had longer to evolve separate from one another. And then that productivity, you have this really high productivity in this area. So that's a general pattern that is often very true. And if you look at species diversity overall, it's typically highest around the equator. But it's not a universal pattern. It can be different in occasions. This is a great example of that. If you look at the latitudinal diversity of seabirds, they actually do something different. They have a lower diversity near the tropics than if you go to the away at higher latitudes in the southern hemisphere or the northern hemisphere. The probable reason for this is related to this productivity argument. Turns out that oceans at these higher latitudes or mid latitudes, mid to high latitudes, not at super high latitudes, but they're more productive than in the tropics, because in the tropics, the ocean warms up a lot. That creates a very light layer of warm water on the sea surface that stops circulation, up-down circulation. And so that warm blanket of layer that is trapped, it becomes quickly depleted of nutrients by plankton, etc., that are living there. And there's nothing to refresh it. When you move to higher latitudes, that breaks down, okay? There's more availability for circulation from deep bottom water with high nutrients, and therefore you get higher productivity, okay? Also during the summertime, it has a really long day length, so you get high productivity, especially then. So it's thought that that's what's causing that opposite pattern in global sea diversity. Seabird diversity, right. Okay, summary notes for that are available that you can access when looking at, you know, when you're going to go through your exams, etc. Okay, but I'm not going to go through those in detail now. What I will do instead is move on and just get us thinking about the next lecture, okay, which is chapter next in the book, chapter 53 on populations, okay? I'll just give a sort of general introductory of where we're going to go. No eye clicker today, no. I'm really trying to concentrate on trying to move on, okay? So when we talk about populations, the sorts of things we're going to consider in this lecture. First of all, what is a population? Okay, what do we mean by that? When we consider the number of organisms living within a population over time, they change. What is it that makes numbers go up? What is it that makes numbers go down? Okay, and why aren't they just stable the entire time? How are populations different from one another? And how can all of this be used in terms of conservation biology, in terms of, for example, sustaining healthy fish populations so that we have fisheries, etc. Okay, those are some of the aspects that we're going to consider in this lecture. So let's start off with that is a lot of penguins. Exactly, that's related actually. You know, in that behavior lecture, I talked about the emperor penguins all marching off to breeding, etc. That's related to that. Okay, so what is a population? So a population is simply a group of individuals of the same species within a given area that have the potential to interbreed with one another. Okay, so if you can't interbreed, or you're just physically separated in some way from other, even if they're the same species as you, if you can't interact and breed within them, then you're considered to be in a separate population. Okay. What do we mean by population dynamics? That refers to the fact that these populations vary and change over space and over time. Okay, over space, that means that maybe where they live now might be different from where they lived before. If you go fishing along the coast here, there are some species that you encounter, either didn't encounter before or encounter much more frequently than you would have done like 40 years ago, such as black sea bass, for example, because conditions here are warmer than they were 40 years ago, and some of those species have shifted in space. Also in time, okay, population numbers, some animals were extremely abundant at one time, but now very rare, or vice versa, okay? So understanding population dynamics is important if you obviously want to conserve something, or if you want to manage it. If it's a species that you harvest, but you want it to be sustainable, then you need to understand the processes that are driving those population dynamics. Okay. Variation of populations in space. So populations exist at different spatial scales. So we talked about ecology, and in general, spatial scale, a lot of ecological work is trying to integrate across different spatial scales and understand how they interrelate with one another. So if you consider a population, this is an example from the book of this plant that lives, it has a geographical range. So where on Earth does this organism occur? This particular one occurs in Nebraska, Kansas, and Missouri, okay? But you couldn't necessarily go to any spot in those three states and there it would be. There's a spatial pattern to it as well. This species lives on, I think it says in the book, on chalky soil areas. So where it occurs is dotted around based upon where they occur. So you have a group of interconnected populations. These are so-called metapopulations, okay? So metapopulation is a group of interconnected populations. So you're effectively a population, but occasionally there might be migration between those. Would this definition of population based on breeding potential apply to plants? They pull on the seeds. Well, yeah, so this is that question. This is where the metapopulation, it can be animals and plants, where the metapopulation concept comes into play. So it's like a halfway house. So the population is what you're sort of typically interacting with, but occasionally an individual or a pollen or something might jump from one area to another. Okay, and maybe it can in some years, but not in other years, depending upon wind direction or something, right? So you lead up to this sort of whole network of interconnected populations making up this meta population. And within a population, then there's also a dispersal pattern. So in some areas, if you consider like a schooling species of fish, for example, they occur clumped. You can go to one area of the ocean, there might be nothing. You go to another area where a school is, there's a gazillion of them there, okay? So highly clumped. In some areas, you might have regular distribution. That might occur, for example, you have, territorial bobcats, for example, that, I keep my territory here, you keep yours over there. Yep, it's 1:30, I'm going to finish this slide. Or you could have random distribution, which is a rarer, more rare in nature. Okay, so as somebody pointed out, it is 1:30, and here is where we're going to take off the next time. Okay, great. Thanks very much indeed. That's okay. Good. And so I'm just trying to press on here, and if you've got any questions, let me know. Office hours, 3 o'clock, sorry, 2 o'clock, link through Blackboard. Okay. Just in case anyone is doing office hours and sometimes I don't see people in the waiting room. I don't know why. You can drop me an email if you're there and you think I can't see you. Okay, great. Thank you very much.
Professor?
Yes.
Yes, just a quick question. What was that general rule of thumb that you went over when we were talking about the Coriolis effect? So I get that at the equator, you move, it's moving faster.
So as you're moving away from the equator, you move ahead. That's how I remember it. So A for away and A for ahead. Okay. So in other words, if I'm in the equator and moving towards Canada, I'm going to move towards the east, so towards Europe. Okay, moving ahead because the Earth is is rotating from west to east. Okay, so let me just see if I can pull up that slide. Whereas if you're doing the opposite, let me just close down this thing. Do I still have the other one open? No. 52, that was this one. Okay, this Coriolis effect. So are you still there? This is the slide that you're talking about, I think, right?
Yeah. I kind of lost you.
Yeah.
A for away. I'm sorry, if you could just repeat that.
Yeah, so if you're moving, so let's look at this little part here. Okay. If you're moving, so in this part of the Earth here, for example, the width, along the surface of the Earth, in a very general sense, the wind patterns are going along the surface of the Earth,
okay,
away from the equator, right?
Right.
So as it's going away from the equator, it's going ahead because the Earth is going in this direction, so it's moving ahead. Okay, A for away, A for ahead. Here, see the pattern in between 30 degrees and the equator. This pattern, this Hadley cell, is moving towards the equator. Okay, and as you move towards, you move behind. Okay, behind meaning a tush, so T towards and T your tush. Okay, moving behind.
All right, got it.
Okay, yeah. So check out the video again because it's difficult to visualize all the time, right? But basically here, if I'm moving from here in this direction, as I move in this direction, the Earth is getting relatively slower underneath me. But I've got the momentum I had from here, so, going far. I'm moving faster here, like that, than if I was moving here, where I'd be going slower. So not only am I going like that, but I'm maintaining some of that momentum that's like taking me ahead like that. Okay.
All right, great. Thank you so much, Professor.
It takes a lot of thinking and visualization, basically. But yeah, okay. Sorry, was that Rodney I was speaking to, or somebody? Rodney, I can see you. Oh no, Ileana's got her hand up.
Hi, Professor.
Whoever wants to ask. Hi.
I have a question. So you said the last homework is due next week, Wednesday, or next week, Monday night?
So next week, I've set 2 achieve assignments that are they'll appear, I think, at 2 o'clock or something, sometime this afternoon. So one is due on Monday night and the other is due on Wednesday night, and then that's it. So for the 2 lectures next week, you have home assignments. For the 2 lectures after that, on May 11th and the 13th, which is the last 2 lectures of the semester, then there are no assignments that I've set. Okay.
Okay. So next Wednesday is the last assignment, basically, right?
Correct. Yeah.
Okay.
2 next week. The last one is due on the Wednesday. Okay.
Okay.
And on it, I've written for the title of it. I've said this is your last homework assignment or something like that.
Okay.
So
Thank you so much.
you'll see. Okay.
Thank you.
Great. Okay. Anybody else out there still got a question?
Yeah, hi, Professor. I do.
Hi.
What's an example?
Is that Sean or who is this?
Yeah, Sean. What's an example of a species that has random distribution?
I can't think of one off the top of my head. And it can also depend on what scale you look at as well. I mean, I know that when you look at as you zoom in closer and closer, the pattern that you see can change as well. I don't know. I can't give you. I'm sure if you Google it, you might find an example. Not sure. Sorry.
Got it. I'll look it up. But someone in the chat said birds
Maybe
or penguins. Would those be
maybe that
birds or penguins?
No, it probably depending upon different parts of the life cycle. Like during the breeding season, yes, very clumped. Probably when they're feeding, they'll be clumped as well because they tend to go to ocean fronts where there's a high productivity area, so they forage in a similar area. So yes, I'm suspecting clumped. Yeah.
Okay, awesome. Thank you. Have a good day.
Okay, no worries. Hi, Nathan.
Hi. So I have a question about evapotranspiration and like heat dissipation. So the textbook states that rainforests have a higher albedo, which leads to a cooling effect through evapotranspiration versus like a dried out desert with light colored sand. Is that correct?
So albedo is different from evapotranspiration. That's the reflective effect, right? So clouds reflect sunlight. That's an albedo effect. Like the ice sheets at the poles, they reflect solar energy. That's different from the evapotranspiration effect that you're talking about, right?
Oh, I thought because the rainforest has a higher albedo, so it can absorb the heat, and that creates like cooling clouds.
No. So the rainforests have a relatively, compared to the land, if you were going to clear the rainforests, let's have a look. Okay, we're on this one. Oop, wrong one. I was on the correct one already, sorry. Just trying to find where that slide is. That's here, right? So let's look at this. So here you can see on this slide here, okay. Am I still sharing my screen? Maybe I've taken it. Can you see that or not?
No, I can only see your face.
Okay. Okay. You don't want to see that. You want to see my screen. Let me just share. I think I've stopped sharing. So. Okay. There you go. Is that better?
Yes.
Yeah. Sure. Okay. So, and can you see my pointer, or do I need to put the?
I can see your mouse.
You can. Okay. So here. So this that I've sort of shaded over as if it's forested, and here it's deforested. You can see that this is a higher albedo, when you clear the forest, right?
Mm-hmm.
Because it's more reflective. So you're cooling, you've got more cooling from that reflective, or you're not absorbing as much heat in the first place, basically, because you've got higher albedo than if you're like dark green forest. You've got some reflection going on, but not as much as this. If you're on a desert, you've got an even higher reflection, right?
Okay.
The big difference here is the evapotranspiration is really high with the forest, but very small without the forest. That's the major difference. Does that make sense?
Yeah, could you explain exactly how evapotranspiration makes something cooler?
So, you know, the way that we cool our bodies is through sweat, right?
Right.
And that's because, you know, when we sweat, moisture goes onto our surface. And as water turns from, as it evaporates, as it turns from a liquid into gas, you get the latent heat of evaporation, right? So it requires, as it transforms from a liquid into a gas, there is a cooling effect that that occurs, okay, because of that transition from a water to a gas to a gaseous stage, and so that is taking heat away with it, so it's cooling. Okay, so it's the actual evaporation of water itself that is creating a cooling effect. That's how sweat works, and that's what's happening in, you know, that from the leaves of a forest. There's water that comes up inside of those leaves, then it goes through the stomata and it evaporates and goes out, and as it does so, it creates a cooling effect.
Okay, I get how the process of evaporation transfers heat away from the ground, but because the forest is dark green, so it reduces the amount of heat and light that's reflected back into space. Doesn't that mean the overall temperature of the planet is getting warmer? Because it retains more energy from the sunlight?
What does the forest?
Or the planet as a whole?
I'm not quite sure if I understand your argument. So there's a whole load of balancing effects going on. So some of it is absorbed by, you know, that's in this figure here, okay?
Mm-hmm.
So there's a whole load of different things going on. So some of it is reflected, okay? That's the albedo effect. It hits something that's reflective, never warms anything up, and goes away again. And that's it, you know, it's done. So about 30% reflected. About 20% of that is absorbed by the atmosphere, okay, and warms the atmosphere. And the rest is absorbed by the surface of the earth, okay?
Okay.
And then that is radiated. Now, here's the outgoing radiation. So what's happening here is you've got a balance between this incoming radiation that is either warming the atmosphere or warming the earth, and then that is going back out again towards space. So it's emitted by the atmosphere, that's absorbed by the atmosphere, emitted by the atmosphere, or it's emitted by Earth, okay? And then it interacts, as this long wave radiation is reflected back out. It interacts with these greenhouse gases, right? Mm-hmm. And instead of just going directly out again, these greenhouse gases scatter it again in all directions, some of it back down to the Earth, and it warms us up. So it ends up being a balancing effect, okay? So our ultimate temperature that we see, and is it shown somewhere? It shows the temperature of what Earth would be here. So, you know, so we're plus 17 degrees Celsius on average globally versus minus 18 as if we didn't have the greenhouse gases and atmosphere. But it's a balance. So some stuff's going back out to space, some stuff's coming in, and the balance between those, you know, like your bank account, basically, you're earning some stuff hopefully, and you're spending some stuff, and if one equals the other, then your bank account is stable, right? So this gets to a stable position. Now, if we increase carbon dioxide, for example, you're going to increase this effect on and reduce that, so it comes to a new balance. Okay, so it's
Okay,
all of these counteracting forces or interacting forces is a better way of saying it. Okay, balancing one another out.
okay, I get it. So one last follow-up question. Is that why Mars is much colder than the Earth, because it doesn't have an atmosphere to help it retain the heat?
I'm guessing so, yes. I'm guessing so. I don't know. Yeah, not sure, but I'm guessing that's a major part of it. I don't know the gas composition of Mars and the solar heating and things like that, but it must play some kind of a role in it, surely. So I don't know. That's a googling job.
All right. Well, thank you for clarifying.
Okay, good. I hope
Have a
that
nice
helps.
weekend.
Right. Cheers. Bye.